Welcome to Unit 4 of GIS for Disaster Risk Reduction, where we'll explore the ways in which hazards are mapped, explore some of the sources for this data available in the community, and consider approaches to mapping hazard areas to a degree sufficient to initiate our work. Upon completion of this module, students will have a good understanding of hazard mapping approaches and be able to develop strategies for some basic mapping of hazard areas in their communities. Natural hazards are bound by physics and behave according to its laws. They may seem chaotic and random, but they're not. To a larger degree, they can be anticipated in general, and when conditions are right, have early warning issued to save lives and property. The co-location of hazards and vulnerability can be cause for a disaster, but only if the resistance of the asset to that hazard is exceeded. So disasters can only take place when hazards occur that exceed the engineering design parameters of our infrastructure and buildings, assuming we've evacuated all our people. So for hazards, intensity and location are critical elements that we will need to consider in our approach. To that end, the hazard extents provide the location, the intensity provides the power, and the hazard dose is an observation of that cumulative power over time. For simple studies, the hazard extent can be mapped to identify where the event occurred. The GIS can be used to identify those assets that were exposed to the hazard but cannot tell anything more about it. The standard example is of a river flood. A simple polygon of inundation can show where the flood was at its peak, but it does not show the depth or velocity, which would be critical to understanding its impact on any one structure or asset in the flooded zone. Intensity mapping would provide the depth and velocity as described in our example, and it's often defined in terms of its maximum in order to understand the peak of its power. With an understanding of the construction techniques used in building stock, we can make some assumptions about how much damage would be inflicted based upon the intensity mapping. Taking it one step further, looking at intensity over time, you can provide a hazard dose reading, which, staying with our flood scenario, may be important. For example, if the flood lasts and the building succumbs to mold infestation, leading to expensive remediation efforts in addition to physical repairs. Another example is ground shaking. Some earthquakes last longer than others, and even if their peak intensity is lower, the fatigue placed on the buildings by the longer shake could cause comparable damage to a larger quake as measured by intensity alone. Probabilistic mapping is a process used for strategic planning to assess the likelihood of a certain event of a certain intensity occurring over a certain time frame. For example, click on the map to the right to go to a USGS page where you can select from a range of time and intensity scenarios for earthquakes. These are typically created by collecting data on the hazard over long periods, recording these patterns, and making some assumption about the likelihood of the pattern repeating. These are often represented as vector contours or raster data layers, and can be very useful in disaster risk reduction efforts, but often require considerable research and effort to produce. These are the types of products that would be generated in a later spiral of development. Let's take a look at some of the more notorious disaster types and break down the aspects that differentiate them and explore some of the sources of this data. Despite promising research, earthquakes still occur with no immediate indicators or notice of their initiation. They are tectonic or geologic in nature, and they cause harm to the built environment through a number of mechanisms, including ground shaking, ground rupture, landslides, subsidence, and tsunamis. We typically map these events by showing the epicenter, or the location of the surface of the Earth, or the location on the surface of the Earth above the hypocenter, where the quake actually started. We'll also use maps generated from models that show the intensity of ground shaking. This map product is called a shake map and is produced by the United States Geological Survey, or USGS, for all major earthquakes around the world. It's a modeled expression of where shaking was likely to have occurred, and it's made from their global sensor network of seismographs and geospatial models that predict the propagation of energy from the epicenter, taking into account the geology of the impacted area. Click on the links in the slide to explore some information on shake maps and other earthquake-related data. The pictures in this slide, starting from the left, show ground rupture, the actual cracking of the earth and the consequences on the building in the background, subsidence, showing where a coastal park sank beneath the Sea of Marmara in Turkey in 1999, and a recent earthquake-induced landslide in Japan. These are two map products leveraging the Shape Map product from USGS. Both maps use the Shape Map in the GIS to capture some estimates of exposures within the affected communities. Tropical cyclone is another complex disaster type that unleashes a range of hazards that can cause harm to a community. Typically, wind, flooding, coastal surge are the most feared elements, but landslides and tornadoes can also result from these storms. Fortunately, thanks to modern meteorology, we now tend to have sufficient lead time to stabilize much of our infrastructure and evacuate most of our citizens. The dynamic nature of these storms make mapping a complex process, and they often require interactive maps with frequent updates to static maps. Mapping is typically focused on one location. Past and modeled path, wind fields, confidence or error cone, and a number of tools for flooding and surge. The most reliable and accessible data tends to be from the U.S. National Hurricane Center, where they integrate sensor readings from buoys, aircraft, ships, and land-based weather stations with satellite imagery and other sources. Here are some examples of the power of these storms, including major wind effects, landslides, and impacts on housing and schools. The tool on the left is called HurAvac, and it provides a number of utilities, the most useful being the mapping of the track and wind reports. For disaster risk reduction, the most useful element is that it retains a catalog of past storms, which can be used for modeling impacts based on past events. Floods can happen quickly or take time to accumulate and are typically, excepting in the case of dam failure, associated with meteorological extreme events. They have a range of manifestations and can trigger landslides. They are mapped in terms of inundation areas, and in a DRR context, often mapped in terms of extent for a return period, such as a 1% chance or 100-year flood. Sophisticated models are available and can be freely downloaded. However, they require detailed inputs to run with confidence. Some organizations, like the Dartmouth Flood Observatory and UNISAT, can provide flood inundation extents in a crisis and access to historical events for DRR planning. The pictures above demonstrate the nature of floods in communities, showing simple inundation, intense flash flood, and infrastructure consequences. These two products demonstrate flood mapping techniques from satellite imagery. The graphic on the left shows the combined high water mark for a long-duration flood that greatly impacted Pakistan in 2010. The imagery collection was timed to coincide with the high water mark over the areas where there were stream gauges in order to help the Pakistani scientists understand how the gauge readings translated into inundation. Volcanoes rarely erupt without some sort of warning, which if heeded can minimize the loss of life. Volcanoes also unleash a range of hazard mechanisms, including ashfall, lahar, pyroclastic flows, and others. Following a series of avoidable tragedies, including the Nevada del Ruiz eruption and resulted disaster in Armero, Colombia in 1985, the world took notice and took this hazard more seriously. These images show, starting in top center, Mount St. Helens erupting in the U.S. in 1980, creating one of the largest landslides ever observed. On the right, a pyroclastic flow chases down a fleeing car. On the bottom, the rescue efforts in Armero in 1985, when the lahar was generated by a small eruption that melted part of a summit glacier. And to the left, Cotopaxi in Ecuador has recently resumed volcanic activity after a long quiet period. The map on the left was produced from a range of technologies, including GPS survey and thermal imagery. See the details on the bottom. The map on the right shows the volcanic flow history of the Nyiragongo volcano and could be used for identifying areas at risk for future impacts. Tsunamis can arrive on the shoreline near the epicenter of a major earthquake in minutes, or take hours to cross an ocean to impact distant communities. The mechanism itself is uncomplicated, an ocean surge. However, the coastline and bathymetry of the ocean can make the behavior hard to predict. There's not much to map in these events in a disaster risk reduction mode other than the extensive past events and the source areas of earthquakes that could generate them. For most communities, building walls sufficient to stop a tsunami is not practical, so the strategy is early warning and evacuation. Thankfully, tsunamis are still rare, and recent events have shown the world that early warning systems need to be in place with all at-risk ocean basins. The graphic on the right shows a before and after image of a neighborhood in Indonesia impacted by the 2004 Indian Ocean tsunami. The images on the left show the surge of the tsunami exceeding the design limits of the seawall and entering the town. The bottom left picture shows the catastrophic impact and the bizarre impacts that such an event can leave behind. The hazard map, though it looks sophisticated, is simply showing the low coastal areas that might have been inundated following the tsunami. It was made prior to other observations being mapped and was designed to inform the potential magnitude of the event. This sort of simple analysis can be useful for the initial risk assessment proposed through this methodology. Mapping hazards can take a lot of time and energy. It will be important that you select the most relevant hazards to your community, and after that, perhaps the easiest to delineate to help you demonstrate the process to the community and begin delivering value. Each hazard type creates challenges for hazard mapping, but there are many expert resources online that can be leveraged to strengthen your understanding. Hazard mapping can start out coarsely in this effort and be refined over time. It will be easier to advocate for investments in hazard maps if you have a clear vision of your purpose and the long-term utility of them. In course sites, find the Lab 3 folder and complete the assignment as instructed. This activity will introduce you to the features and capabilities of Google Earth. Will it also introduce you to the skills needed to extract information from satellite imagery and demonstrate the overall concept of using GIS for DRR planning. Thank you for completing the Unit 4, and don't forget to take the short quiz relating to this course on course sites. Thanks again.